Welcome to the Explainer. Okay, today we're tackling a massive, honestly kind of daunting transition in your software engineering journey. We're talking about making that huge leap from writing single lines of code for simple apps to actually architecting massive enterprise-level systems. I mean, seriously, ask yourself, how do you map thousands of classes without completely losing your mind? Standard class diagrams, yeah, they are fantastic for small apps. But the second you hit real scale, they fail entirely. They literally turn into this unreadable, tangled web of spaghetti lines. And that is exactly why we need to master the big things in Unified Modeling Language, or UML, to take back control. So here's our roadmap for this explainer. First, we'll explore the macro world of UML, then look at components, see how to chunk things up with subsystems, organize it all using packages, and finally map it to physical reality with deployment diagrams. Let's dive right in. Section 1. The macro world of UML. Let's look at the foundational split and how we conceptualize large systems. Basically, UML gives us two distinct flavors of solutions for scale. On one side, we have structures that actually represent the architecture itself, things like components and subsystems. These are the physical building blocks of our software city. But on the completely opposite side, we have big things used purely to zone and organize that massive structure, like UML packages. Think of it like the difference between the physical crane actually building the skyscraper and the filing cabinets in the office storing the blueprints.
Which brings us to Section 2, Components, the building blocks.
So let's start with the structures that represent the architecture. Think of components as your highly advanced, totally replaceable Lego bricks. The official UML 2.0 spec defines a component as a modular part of a system that encapsulates its contents and whose manifestation is replaceable within its environment. But honestly, I love the source's description that a component is just a structured class with aspirations. Because it encapsulates its internal workings so perfectly, you can easily swap it out for another component as long as they both support the exact same protocol. It is the absolute definition of plug-and-play architecture. Now, what's really interesting here is how these two essential views are visually juxtaposed, the black box view and the white box view. Look at the black box view on the left. Everything internal is completely hidden. All you see are the provided and required interfaces, basically what it gives to the system and what it absolutely needs to function. But over on the right, that white box view exposes the internal realization. It shows you exactly how the component uses internal classes like Class B and Class C to actually realize the interface it's providing to the outside world. As an architect, you'll be constantly zooming back and forth between these two perspectives. Moving right along to Section 3. Subsystems, architectural chunking. So, how does all this build up to massive scale? Well, when components get too large, we graduate up to subsystems. A subsystem is essentially a massive component acting as a unit of decomposition for a larger system, right at the absolute highest level of abstraction. These are your major architectural chunks. They use ports and interfaces to connect together and create a unified system architecture. But here's the crucial distinction you absolutely have to remember. Unlike your standard physical classes or basic components, subsystems are purely logical constructs, meaning they cannot be instantiated directly at runtime. Let's ground this theory in a really brilliant example, the Acme spacecraft architecture. Look at how this incredibly complex, massive system is broken down. Instead of a tangled mess of code, we have clean, distinct subsystems, things like thermal management, power management, and navigation. By clustering all that chaotic code into these high-level architectural chunks and then wiring them together through clearly defined interfaces, an architect can actually stay sane while designing a literal spaceship. It just gives you perfectly manageable boundaries. All right, Section 4, Packages, the filing system. We're shifting gears now away from structural components to pure organization. If components are the engine parts, packages are the neatly labeled filing cabinets in the design office. A package is a general-purpose grouping mechanism used to define a semantic boundary in your model. You can think of them strictly as design-time folders used to group related UML elements. And they serve a highly critical technical function, encapsulating a namespace. This is what effectively prevents naming collisions when you have hundreds of developers working on the exact same project. And if you've been there, you know what a total nightmare that can be. Inside these folders, we have some pretty strict zoning laws regarding visibility. It's elegantly simple, though. You just label a package element with a plus sign to make it public. That means those elements are exported and can be used completely outside of the package. Conversely, you use a minus sign for private visibility. Private elements are strictly internal. They can literally only be used by other elements sitting right there inside the exact same package. Perfect organizational encapsulation. And the cool part is, you aren't just limited to flat folders either. Notice the nested packages mapped out here? You can visually represent this by literally drawing boxes inside of boxes, or by using the containment relationship, the one with that little anchor icon. This containment visually and neatly folds away the complexity of a system. For example, you can hide a nested member details package completely inside a larger membership package until you actually need to zoom in and see it.
So the really crucial point here is grasping how these packages rely on each other, their dependencies. This matrix breaks it down beautifully. For instance, an import dependency means the public elements of a supplier package are added as public elements to the client namespace, seamlessly. But an access dependency? That one is much stealthier. It adds those public elements of the supplier as private elements to the client, meaning they aren't passed on any further down the line. Understanding these exact semantic rules is what stops a massive enterprise project from turning into a chaotic free-for-all.
Section 5, Deployment. Physical reality.
Okay, it is finally time to bridge the gap. We are moving from our abstract, logical software world into the messy, physical reality of actual hardware. Because everything we've discussed up until now, the components, the subsystems, the packages, that's all been purely logical design. But our software actually has to live somewhere, right? Deployment diagrams model the exact mapping of the software pieces of a system directly to the hardware that's going to execute it. This is the final step in the architect's journey. It's translating your pristine, logical design model into a concrete physical implementation model.
In this physical world, our logical components manifest as what we call artifacts. An artifact represents a physical piece of information. Notice how the logical book and library components physically manifest into a real-world artifact, like librarysystem.jar. And just like your logical components, these physical artifacts can contain other artifacts and they can depend on one another. You might even have one generic artifact, but then deploy multiple instances of it across a bunch of different web servers. To help with this, UML2 provides a standard set of stereotypes to easily categorize exactly what kind of physical form your code takes. As you can see outlined here, an artifact could simply be a generic document, a raw source file, a script to be executed by an interpreter, a compiled executable program file, or a library, like a dynamic link library or a Java archive file. Tagging your models with these specific stereotypes removes literally all ambiguity for the engineers who actually have to deploy your system.
So where do these physical artifacts actually live? Well, they live on nodes. A node is a physical entity that can execute artifacts. Basically, they are your actual computational resources. And nodes come in two main flavors. First, you have a device, which is a physical machine capable of calculations. Think of a Windows PC or a bare metal Linux server. Second, you have an execution environment, which is a software configuration hosting specific artifacts, kind of like an Apache web server living inside that physical Linux device.
And this master blueprint right here brilliantly illustrates our entire journey converging into one. Here you see the full picture, a client Windows PC device communicating over a defined path to a server device. Inside that physical server is a JEE execution environment, and that is actively hosting the converter app.earjar artifact. This single diagram tells everyone on the development and ops teams exactly which physical server is running which specific piece of our application's architecture. No guessing required. Which brings us to a provocative final thought for you to take away today. Does your system's actual architecture match the code, or is it a tangled, unreadable mess? If you're struggling to scale, it might be time to step back, grab a whiteboard, and draw some new blueprints. By leveraging these macro UML techniques, from encapsulating your components and chunking subsystems to structuring clean packages and mapping the whole thing out in a deployment diagram, you can genuinely tame even the most overwhelming code bases. You possess the tools to turn a chaotic sprawl into an elegantly structured software city. Thanks for joining me on this explainer, and hey, happy architecting.